Welcome to this lecture series in group theory. In this lecture, we'll look at an abstract construction which allows us to construct a group out of two different groups. Here are the problems. I'm not recalling anything from the last time because we don't need it for this lecture. So these are the problems. And okay, let's get started. This is going to be a short lecture, or so I think. So suppose we have two groups, G and H, and I have denoted the binary operations as star and diamond. So then what we want to do is we want to define a group structure on the Cartesian product of G and H. And for that, first we need to define a binary operation, and this is how we define it. So we pick G1, H1, and an element from the Cartesian product, and another element G2, H2 from the Cartesian product. And we send it to, well, we just operate star on G1 and G2 and operate star with star on H1 and H2. So this is G1 star G2 and H1 diamond H2. So this is the binary operation. And even though we have done this in such an explicit manner, in general, what we would do is we would suppress the star and the diamond. So what we would see is, from now on, what we would see is just G1, G2 and H1, H2. And it will be clear from the context that, one has to be aware that this H1, H2 are elements of H. So the binary operation used is the one that is defined on H, and G1 and G2 are from G. So the binary operation here is the one which is on G. So this is how we will proceed, because every time writing star and diamond is very cumbersome. All right, so this is just a binary operation. So we'll check that this is indeed a group. So we need to check associativity, which is very easy to check. All of this is very easy to check, but let me do it. So let G1H1, G2H2, and G3H3 be three elements chosen from the Cartesian product. Then we have G1H1 operated with or multiplied with G2H2. This is equal to, so first we are multiplying these two together, and then we are multiplying that guy. So this is by definition equal to G1, G2, H1, H2, which is multiplied with that. Again, when I say multiply, I mean the group operation. Don't think of the multiplication of real numbers. I've said this so many times that you might be getting bored of it. Anyway, so this again is by definition G1, G2, and let me put a bracket here, G3, and H1, H2, let me put a bracket here, H3. But now we use associativity of the groups G and H, and this we can write G1, G2, G3, and this one as H1, H2, H3. And this becomes, by definition of the binary operation that we defined, equal to that. Which is equal to G1, H1 times that. Yeah, so this is what associativity means, and therefore we have checked associativity. Now let us check identity. Identity, well, if this is the identity of G and, or let me write, if this is denoting the identity of G and this is denoting the identity of H, then EG, EH times GH. So G and H are some arbitrary elements of G and H respectively. So this is equal to EGG, EHH, which is equal to GH, because EG is the identity of G, which is equal to GEGHEH, which is GH operated with EGEH. So we see that this guy is the identity of the product, the Cartesian product. So it has an identity. And inverse. So if G comma H is chosen arbitrarily from the Cartesian product, then what we do is we just check that this G inverse H inverse, since G is a group, this guy, the inverse of this guy exists, and that we write like this, and the H is a group, so the inverse of this guy exists in H, and we write it like that. And we'll just check that this is equal to the identity we just discovered. But that's clear because this is equal to that, which is identity of G, identity of H, and that is also same as G inverse H inverse GH. So inverse of every element exists, and therefore the conclusion is that this thing is indeed a group. G cross H is a group under this binary operation, and that's about it. Maybe let me make one small remark which is trivial, but let me still say it, that if mod G is M, some finite, let's say G is a finite group and its size is M, this size is N, then G cross H has size what? Well, M times N and Mn. So that this has nothing to do with group theory, this is just a set theoretic fact. But the point is that if we have two groups, one of size M and another of size N, then we have a way of constructing a group of size this. That's the product of the sizes. So this is one way to put two groups together and create new groups. So for instance, we have seen groups like Z mod NZ, and we have seen dihedral groups. So we can consider groups like these. We can consider other groups, like we can cross, just pick two groups and cross them, and that's another group. Or you could also do, three wise products. So if G, H, and K are groups, then you can also take threefold Cartesian product and define the group structure on this similarly. Or you can just think of it as the group G cross H crossed with the group K. So it is the direct product. Yeah, so I should have said that. This is called the direct product. This construction is called direct product. Let me write it here. G cross H is called the direct product with the binary operation that we defined, that I am leaving implicit, is the direct product of G and H. So this is called the direct product construction, and you can, it's not that you can do it only with two groups. I give you a bunch of groups and you can still define the direct product in the very same way. Alright, so this is all for this lecture. There's nothing much to say. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.